Team lecture, I start for about 20 minutes, and then Bill's going to finish the last 20 minutes. So let me just remind you what we finished with last time. So last time we dispensed with unitarity of irreducible principal series. And that was the these two pictures. I'll just draw this picture. The spherical.
Excuse me for a minute. Is Mac in your office?
Yes. There was the cross coming from the even irreducible principal series, and then just the line from the odd irreducible principal series. And we also, the first thing we started was with the finite dimensional ones, right? We said that the only finite dimensional ones that were unitary were the trivial ones. But let's actually revisit that, because that will be important. So one of the last things Bill did in his lecture this morning was using the lowering and raising operators to compute the zero n homology V mod NV for the finite dimensional. So let's let F equal d-dimensional finite dimensional. Then you can compute F mod NF, and this is isomorphic as an MA module. So remember, M is this group that's plus or minus the identity, and A is isomorphic to R plus. A is connected in my notation. And this was isomorphic to as an MA module to the character, which took plus or minus the identity times A inverse to, I think it was minus the parity. Well, it was just the parity of D minus 1. That's the sign that we put here. And then the character of A was A to the 1/2 minus D plus 1. Strange way of writing it, but I'll write it like that. Or actually, I think for that to be correct, put halves there. Okay, so we know we can use the, what does this tell us about matrix coefficients, say? So this tells us that the leading exponent in the matrix coefficient expansion, in Harish-Chandra expansion, of the matrix coefficients for a finite dimensional one is just this guy. So it's 1/2 minus D plus 1. And, well, yeah, so this function A to the 1/2 minus D plus 1, that blows up at the origin if D is bigger than 2, right? So it blows up at the origin if D is strictly bigger than 1, say. D is bigger than or equal to 2, it blows up at the origin, so that means it blows up at infinity. So, so the matrix coefficients blow up at infinity unless D is equal to 1. So that's another proof that the trivial representation is the only unitary representation, right? Just the trivial representation, the matrix, well, it's obviously unitary. Any representation whose dimension is bigger than 1 has unbounded matrix coefficients. Okay, not so interesting, but let's make one more other conclusion. We had this version of Frobenius reciprocity, which was Hom MA of F mod NF into okay, so say sine tensor A to the nu tensor 1, which was isomorphic to Hom GK of F into some unnormalized principal series, which the script sine tensor A to the nu tensor 1. So what this implies is that, well, this is a one-dimensional space. So it says that F embeds into a unique principal series. Okay. So now let me switch notation back to the normalized principal series. So this implies, well, since we computed the computation of, I'm just repeating what Bill said mostly in words at the end last time. The computation of f mod m implies that now f embeds into the normalized the d-dimensional representation embeds into the normalized principal series representation. Okay, a n to g. What I put here is I'll put this character epsilon, where epsilon is minus, well, is the parity of d minus 1 tensor. And then there's some shifts involved in the normalization, and what this amounts to is a to the d, let's see, the trivial, so if I put in 1, I'm supposed to get, if I put one dimensionals, I'm supposed to get 1, so I think it's just this. Yes?
What's the word before f over f?
The computation of, so there's a lot of squiggles there. Okay, so the computation of this, we plug that in there, we get embedding of a principal series into this guy, which in the notation on the user's guide is p epsilon, that's this parity of d minus 1 of d. Now that looks a little bit fishy, but if d is 1, that's right. Okay. I think so. Okay, so remember we had the picture we had for irreducible principal series, and it's in the footnote of the user guide, is that p of nu is isomorphic to p of minus nu. So if this embeds into p epsilon of d, you might expect it also to embed into p epsilon of minus d, right? So you expect also, expect also fd embedding question mark into p epsilon minus d, right? Does that happen? So there's probably not. So there's some people among you who can read body language reasonably well, so you know the answer. So the answer is no.
Some people speak body language.
Okay. But why? I mean, do you remember anything from these pictures? Some of the pictures had, we had these raising and lowering operators, and the finite dimensional sat in as a submodule, and the what I called the discrete series, we haven't explained that terminology, sat in as the quotient. Once I quotiented out, then we had this. But then the other half of the pictures had these sitting in as the highest and lowest weight modules sitting as submodules, and the finite dimensional is a quotient. And that's exactly what's happening here. This doesn't embed. Instead, this is a quotient. Okay, so is that clear? So you switch the principal series to the negative principal series. In the reducible case, the composition series gets switched. They get inverted, and that's important. Okay, so now we're going to use those observations. Basically, we're just going to turn that around, because in the case where let's say in this opposite case where the finite dimensional is the quotient, that's the case where the discrete series, the highest and lowest weight modules, embed. And that's the only case where they embed. So we use that embedding just to reverse. We have the embedding to get a computation of this n homology for the discrete series, which gives us the leading exponent, which will give us some information about the growth of matrix coefficients for discrete series. So so this is the notation on the sheet, say d plus n. This is this lowest weight module that starts at n plus 1 and goes up to n plus 3, n plus 5, and so on and so forth. Okay? So again, what we saw from those pictures is dn plus embeds into the principal series that the finite dimensional doesn't embed into it. So it embeds into p. This is the same. This is epsilon is the parity of n plus 1 or n minus 1. And then what I put here is n. Is that right? Yes, that's right. Okay. So this embedding into a principal series by Frobenius reciprocity, so maybe I'll call this dagger or something, So this is the unique embedding into a principal series. So the Frobenius tells us says that dn plus mod n. So these n. So we really have to make this a Germanic, Gothic n. This is isomorphic as an MA module to, well, there's some sign here, and the key is this a. Well, it's the opposite exponent, and so it's 1/2 n plus 1. Okay, that character. So is that clear, how we're going back? And so we conclude that the leading exponent of d plus n is 1/2 n plus 1. And actually, there's nothing special about considering the lowest, this lowest weight module. We could have done the same thing for the highest weight module, which embeds. So we just, by the same conclusion, it has the same leading exponent.
Excuse me. So why the letter before the dn plus that there?
Conclude leading exponent of dn plus.
Oh, there. Yeah.
This?
Yeah.
This is n. So this is n homology, n which is there's n which is supposed to be italicized Roman font, and this is supposed to be fracture or Gothic font. So.
Infinitesimal character, that n is the Gothic n, or the same n that is in your sheet here?
On my sheet, this is the n. This is 0th n homology. This is a Lie algebra. On my sheet, no Lie algebras appear. So on the sheet, there's I didn't even have to load in that font package when I compiled it. Huh?
What is LaTeX doing?
Yeah. So, no. This is a key distinction. I mean, n in this picture is just an integer, right? And what we were doing before is like over here where there were only d's, we're taking f mod nf, and that's the Lie algebra. So it's the 0th Lie algebra homology. Okay, good. So thanks for slowing me down. Okay, so as I was saying, all we used is that this lowest weight module embeds. The same goes for the highest weight module, just going the other way. It has the same unique embedding into the same principal series, and so it has the same exponent.
Unique, you say it's a unique embedding, but unique in what sense?
Well, there's no other principal series that isn't equivalent to this one. Well, I mean, there's no other principal series into which this embeds. I mean, this embedding is unique in that sense. Okay, but now we can analyze the growth of these. So at infinity, as x goes to infinity, in a group, the matrix coefficients grow like, well, if they grow like this at 0, they grow like the inverse of that, like x goes to minus 1/2 n plus 1. So notice if n is bigger than, or is strictly bigger than 1, this exponent is bigger than minus 1/2, so it's square integrable. Okay, so they're an L2 of SL2, so they die quickly. If n is equal to 0, I mean, I'm cheating a little bit. Then I haven't done the analysis because there is no finite dimensional representation there. We'll have to duplicate it. But the same computation of the leading exponents holds. So if n equals 0, these are the so-called limits of discrete series. The matrix coefficients of d0 plus minus, well, they grow like 1 over x at infinity. So they just they grow like 1 over, they grow like 1 over the square root of x. If n is 0, this is like the square root of x. So their square is 1 over x, so they just miss being L2. Okay, so they're in L2 plus eta for every eta greater than 0.
looking at the values on A or?
Yeah, we're only looking at the value. Yeah, so I'm being a little bit being a little bit fast and loose. So we're saying that as you go along, as you go to infinity along A, this is how they grow. They're L2, but then these are tau spherical, so that the transformation under K isn't going to change the growth properties. Or when you compute the integral in the L2 norm on G, it'll still be bounded. It's just an integral over. I mean, you have to use the integral formula for KAK, corresponding to KAK. This is finite volume, this is finite volume. This is where all the action happens. So, okay, so let's begin. The KAK integral formula? Yeah. So, yeah, I'm not going to. Yeah, the KAK integral. Yeah. So I'm not. I mean, I think you can trust me that since G is KAK, the L2 on the group, the property of the matrix coefficient being L2 on the group is just determined by what happens in the A direction, which is what we've computed here. Okay, so let's focus on that case. Consider the n greater than 1 case. We have dn plus or minus. So fix one of these matrix coefficients. No, actually, I'll fix v dual in v tilde, or I guess this should be dn plus or minus tilde. And we consider this map which takes dn plus or minus to L2 of G, well, in fact, the smooth L2 functions, which takes a vector in here to the matrix coefficient of this fixed v tilde tensor v. Okay? So this is equivariant for the right action over here, because the representation I have here is dn. And so this is embedding, amounts to an embedding of d plus or minus, well, of the Harish-Chandra module, dn plus or minus into the Harish-Chandra module of L2 of G. So what we're getting is that these discrete series Harish-Chandra, these things that I've been calling the discrete series all the time, now we understand their name because they're appearing as Harish-Chandra modules of things which are submodules of L2 of G. So I don't know a good notation, so this is a bad notation. Write d plus or minus n for the representation of G with Harish-Chandra module dn plus or minus such that dn plus or minus injects into L2 of G. We can do that. We can. This is the Harish-Chandra module. This is some global unitary representation. So what I'm saying is that this Harish-Chandra module comes from a discrete summand of L2 of G. Okay, that's what I'm saying. So i.e., so L2 of G, which contains, well, well, I'm going to. Well, I was going to write some other junk over here, but I'll do it your way. So, like that. So that's why these are called discrete series, because they sit discretely, or the Harish-Chandra modules of things that sit discretely in L2. So they're obviously unitary, right? Because L2 is unitary. So any submodule of unitary representation is unitary. So in particular, dn plus or minus are unitary. So, okay, so we treated the unitary. And so the only case we haven't dealt with is this limit, the so-called limit of discrete series, and we have all the tools to do that too. So let me just tell you about that, and then we'll be done. So maybe I'll just state it as a exercise or exercise in the explicit formulas, explicit pictures, the raising and lowering pictures, which if you take the principal series, which has odd k-types, doesn't go through 0, so the non-spherical principal series, where the Casimir, which corresponds to this parameter nu equals 0. Okay, so in Bill's notation, that's induced from MAN to G. I put the minus representation on M, and I tensor with, well, the trivial representation of A and the trivial representation of N. Actually, is it the trivial? No, it's not the. No, it is. It is. Okay.
Question. Yeah. So I know when you excluded the case n equals 0.
Yes.
This argument, I mean, there's nothing special about n being greater than or equal 1. You could, in this argument, you could possibly include n equals 0 too.
No, because the matrix coefficient is not L2. For n equals 0, right, it just missed being L2.
Oh.
Right? For n equals 0 it was L2 plus eta for any eta positive. But no, I mean, I really wanted, I needed n greater than 1, so it lands in L2. So. And in fact, the d0s don't appear discretely. The d0 plus or minus aren't submodules of L2. I forget how I. Was this the condition? Yes, I think you're right. Okay.
Where did you use the unique embedding of the Harish-Chandra module Dn?
Okay, so I had a unique embedding from the formulas which told me that the dimension of minimal, well, basically dimension of n homology.
Couldn't you get that from Dn modulo n Dn?
Yeah, I could have computed that directly.
So you need not have done the reverse. You could have done it exactly the way you did that finite dimension.
Yeah,
case.
it's a messier calculation because now the n is not a raising operator anymore. It's some mixture of raising and lowering operators. So you could have done it directly. In fact, that was an excellent exercise. I'm sorry I erased that. So another way to compute the, I mean, what were we after? What was the key thing that made this work? We needed to compute the leading exponent and see that the matrix coefficients were L2. And the way we did that is we computed a leading exponent by this algebraic version of leading exponents by computing n homology, so dn plus minus mod n times dn plus minus. And so you're exactly right. Rishi's exactly right. You could have computed that directly with your bare hands. You have the formulas. It's a little bit messier. But since we had done everything, it just seemed like a clever way to get around doing that calculation by saying we have a unique embedding, so it's a one-dimensional space, and we know which one it embeds into. It's the opposite of the finite dimensional. So it has the negative. It has the decay at infinity. But that's a good point. Yeah, so we take this guy, and this, from the formulas, this is the one that there was no finite dimensional. It just broke up. These raising and lowering operators were 0 here, so it broke up into two pieces, which was dn plus d0 plus dn d0 minus. This is one of these unitary, reducible unitary principal series, because this is on the unitary axis. So we conclude that both of these limits are, even though they just miss being L2, the matrix coefficients are L2 plus eta for any eta greater than 0, just they grow like 1 over x. These are also unitary, even though they don't embed into L2. So that explains all the entries on the table, I think. And so if you have any questions or find any other mistakes, I posted the revisions to the table based on a couple corrections that Bill noticed, and they're on the web page, so you can get them. Yeah, so what about p plus at nu equals 0? So that's the one. So this one has. What are the k-types of this? So this has k-types minus 1, 1. This is the non-spherical one, 3, minus 3, so on and so forth. But the other one, p plus, that is spherical. That goes through 0. 2, 4, minus 2, minus 4. And that was one of the ones on our list of irreducible principal series. So that was one of the ones that we treated last time. So this one is irreducible.
You haven't proven that. You just keep telling me the same.
Well, I mean, in some sense, I wrote the formulas down on day 2 or something. So I mean, we do have the raising and lowering operator formulas. So this is irreducible. And then that was what got us a toehold. So in this sheet of the picture, we had this irreducible unitary representation, and we deformed the Hermitian form in an area where there's no reducibility, or equivalently, there are no zeros that were encountered in the formulas that Bill wrote down, and that's what got us this complementary series. So that was a very important point, and its irreducibility, which is the opposite of the negative one, was important because it allowed us to deform out to the trivial representation. So does that answer your question? Okay. Another question? No, just flexing your arm. Okay, so then I'll hand this off to Bill, I guess. No other questions?
I'm not going to use my computer. So I did something very dangerous. I got inspired by Peter's lecture, so I'm going to give you a totally impromptu performance. But it's Friday afternoon. So let me continue. I'm going to tell you almost exactly the same thing that Peter told you, but from a totally different point of view. And I'm not going to do it in the generality because I'm just going to continue. So what I'm going to do is I'm going to continue the example I talked about on Monday morning. I think we'll have a better picture of what's going on now. So let's look again at the example I talked about on Monday morning. So let's look at the unit disk, which is really the upper half plane in disguise. And here's infinity on the upper half plane, which is fixed by P. And here's 0. Here's the orbit of A that looks like this. Here's a point fixed by K. And here, around the outside, is P1 of R. Okay. Now, what I did on Monday was I looked at a basis. We looked at those functions, which are harmonic in the Euclidean sense, because that's Euclidean. In that case, it's the same as being harmonic in either Euclidean or non-Euclidean metric. And this had as a basis 1 z n and 1 z bar n, or n is greater than 1. And it also contained Fourier series. So now what I'm going to do is I'm going to take Fourier series Zn plus, so minus, so here n less than 0, here n greater than 0, and here just these C0. Something's eating the array. Oh, there it is over there. Okay, and there's some convergence conditions. And in this case, I'm going to be very, very precise. I'm going to look at F such that the restriction of F Z bar, excuse me. Yeah, absolutely right. That's right. F such that F restricted to Z equals 1 is C infinity. And now, if I take these functions, so I take my functions in this space, I restrict to this, that's an isomorphism because we know that on the circle itself, we just get the Fourier series, which are infinite combinations of this. So in fact, we can tell what the CNs are here by some condition, some obvious condition somehow on the CNs which guarantee exactly the growth. But that's so we have a map from this space goes to C infinity of the disk, but the disk is C infinity G quotient P. Okay, so now there's a map from this space. I take the de Rham differential. Okay, so this maps to, under the de Rham differential, this maps to sigma. Let's see, the constants get killed, so it's still n greater than 0. It's Cn n times z n minus 1 times dz plus some n less than 0 Cn absolute value of n minus 1 times z bar n minus 1 times dz bar. Okay, are people familiar with this holomorphic, anti-holomorphic differential stuff?
I have a question about your notation.
Yes, sir.
You have F such that, is that
F restricted to the circle Z. I'm just, I'm speaking a little, yeah, I'm. Okay, so there should be like brackets around. Yeah. Does that fix you?
Sort of. I'm unhappy nonetheless.
You're happy or unhappy?
Happy.
Okay. Yeah.
To clarify, you allow functions to have singularities in the disk.
Allow values to.
You allow your functions to have singularities inside the disk.
No, certainly not. It's analytic. It's del equals 0, so it's perfectly smooth. F is C infinity. F is harmonic inside the unit disk.
But how come you have negative powers of C?
No, n is negative. So
Oh, there's an absolute value here.
Oh,
Yeah, that's right. This is. You see why you can see why I give computer talks, because my handwriting is absolutely foul. Look how I'm smiling. It's a shit-eating grin, I tell you. Whoops. Okay.
But
You see, I'm the same in both terms.
no, n is already. Yeah. Indexing C is negative.
Oh, I'm sorry. This is yeah, C. Yeah, that's right. Just checking how you guys know calculus. Okay. But we still haven't gotten to the important point. Is everybody familiar with the holomorphic, anti-holomorphic derivative business? Sarah, are you familiar? You don't look too happy with that. No, so Z is a complex valued function, right? It's x plus iy. And so dz, and so these have differentials. You don't know what a differential is, right? So dz is equal to dx plus dy. That's very simple. And if I have a holomorphic function, then if for example, d of z squared is equal to 2z dz, because it's a holomorphic function. But if I take the opposite of this, it's equal to 2z bar dz bar. And z bar, of course, is dz bar is exactly the opposite. It's the conjugate of this. So it's dx minus I dy. So this is just a formalism that lets you put in the complex numbers in a nice way. Yeah, this is just calculus, but complex calculus with the differential thrown in. So now we're looking at differential. So this is a one form on the unit disk. Okay. And now, well, let's do the first thing. So let's see. So we have a map. We have my space. We have all these holomorphic functions and anti-holomorphic, well, the holomorphic and anti-holomorphic polynomials. Now we take the de Rham differential. The de Rham differential is G covariant. If I apply G and then take the differential, it's the same as taking the differential and then applying it, because the differential is absolutely canonical. And so this is a G map onto the one forms on the disk. So we have a map from my space, which I'll just call del F equals 0, goes to some space. In fact, it's harmonic one forms is what it is. I won't say why, but and unfortunately, this is why I queried Peter's D. My D is a disk. So, but now you've gotten totally used to the fact we all have terribly different notation. Okay, and one forms on the disk with C infinity values again. Okay. And of course, again, taking boundary values commutes. So what's going on the boundary of the disk is simultaneously what's going on boundary of the disk. I'm taking the de Rham differential again, but I'm getting one forms on the projective line. So I have the following fact. I have my space. Let me give a name to my space. H0 equals harmonic functions, and H1 equals harmonic one forms. This is not good notation, but I won't need it very often. So we have the following commutative diagram. And these, in this case, remember, one forms are the same as my densities, so that notation is perfectly okay. And this is a commutative diagram of G spaces. I'm not looking at you because I'm disappointed. I'm looking at you because I'm trying to explain it. Can somebody else volunteer to explain to her what a harmonic one form is? I don't think, the truth is you don't have to know. Okay? You just have to know. So all you have to know is that it's,
Maybe local coordinates, the function is harmonic.
well, no, I mean, yeah, so what it is, it's very simple actually. It's those things which in local coordinates is a combination of a holomorphic differential times dz plus an anti-holomorphic things times dz bar. That's all it means. Okay, so, I mean, what you're seeing is what it is. Okay. I mean, when I take the derivatives, there's only one, there are some harmonic forms missing here, but I don't want to talk about those. There's just one, it's a one-dimensional space of harmonic forms which are missing, but we don't have to know about those. Okay, so we have this map. Okay, now, what I claim is that it should be pretty clear from that the quotient, so we have this quotient, and now, in here we have sitting, so we have the constant function sitting here, and of course the constant functions sit here too, and the constant functions are in the kernel. So this is the kernel in both cases. Okay. Because the only functions whose derivative is identically zero are the constants. Okay, now, you may wonder why I've set this up, but the reason is because you can see immediately that the image forms, that these differential forms that we get here, are square integrable. So the image of D of, well, the image of H0 under D contains only, it amounts to square integrable forms. So equals square integrable differential, square integrable one forms.
Why do we see this immediately?
I mean, you will see it immediately. Okay. You will see it momentarily, to use one of Peter's two uses of the word momentarily. So let's see. Suppose I have a form. Suppose I have f of z dz. And so what's the metric? How do I get a metric? How do I get a G invariant metric on the one forms? It is, but I don't care. They're just if I say they're square integrable, I don't care whether they're harmonic or not. They're just square integrable.
Equals means it lies inside.
They are equal to. They're not all of them. Yeah, they're inside. Yeah. Okay. Okay. So suppose I take a form, say a holomorphic one form, and I want to integrate it. What do I do? Yeah, I make a two. I just make a two form out of it, and integrate that. So this is the G invariant Hermitian metric on one forms, and you can do the same thing with the anti-holomorphic ones. And there are no constants. We haven't seen those. This is a G invariant Hermitian metric. On the one forms. Okay. And so we just integrate this over the circle. So we have f bar equals the integral over d of f of z or d dz wedge dz bar. And this is over the disk. But now what functions do I have? Well, f is equal to it's equal to the constants. Z bar. So these are all finite. I mean, it's iterating it over the disk. There's no infinity, so to speak. The nice thing about this is infinity disappears, so all are finite. Okay? So that's by all means the simplest way to see that the discrete series are in fact discrete.
They're square integrable just because they're continuous on the whole of the closed.
They're square integrable because the integral of z over the unit disk is finite.
Right, so any continuous one form on the closed disk is square integrable because any continuous.
Yes, I guess that's right. Well, no, it has to be continuous and extend to the boundary. Yes. Yeah, that's certainly correct. Okay, because that's the environment. That's certainly right. So you get something. Right. Okay. But the only ones we're looking at, but in general, it's a huge space of G representations. The ones we're looking at are actually ones which are very nice as a G representation. Those are the harmonic ones. Okay. So let me say again. So I have one other point to make. So this is half my point for today. So there's a very easy way to see that the discrete series are in fact discrete by natural geometric. And you can do the same thing for the other discrete series. You have to talk about forms with values and something else. You can't just, or in general, if I can look at some finite dimensional space as sections of a line bundle over the unit disk. And then I take differentials with that has a nice differential and so on. So you're looking at sort of higher differentials. And you get exactly the same argument. It's messier, and this is by far the nicest case. Well, they don't occur here. There's no differential in the limits of discrete series. That's precisely the problem in some sense, actually. Okay. Yeah. What do you mean by discrete? Well, I mean, in this case, it's discrete. So in Peter's case, he said it's discrete in L2 of the group, and in this case, it's L2 of the disk. On forms. If I look at, so let's look at functions on the unit disk, which are L2. Okay. Then what I've shown is that these are square integrable. I'm looking at forms rather, sorry. So we're looking at L2 of one forms on the unit disk. And these things sit in there, and they sit in there discretely because they're square integrable, so I can integrate them against everything else. So they're a discrete summand of the, in fact, you can break up L2 of one forms is equal to these discrete series plus some continuous mess, which we won't talk about for a while. Right? I can integrate any L2 thing against one of these. I can give it an orthogonal component, right? It's equal to this thing I've defined, and these are D plus or minus 1, and plus some complement. Right? So it's sitting in there discretely. Okay. And D is equal to G mod K, and K causes no trouble with analysis, so this shows that they're actually square integrable on G as well. Okay. Okay, so now we've looked at the interior of this. I haven't used the full diagram yet. I just want to leave this part. Yeah. Yeah. These are discrete series. This is the first. This is D1. Peter had D plus or minus 0, which are the other, which are not discrete series. Okay. And I think this is your notation, right? I haven't yet. Right. 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 0 corresponds to the 0-dimensional representation of G. Right. Okay.
One more time how D plus and minus 1 are related to what we just did over here.
Sure, I did that calculation in my first lecture. I showed the up and down operators.
Okay.
Right. Right? Right. Okay. So you've seen, I mean, you keep seeing the same thing over and over. We always give it to it in a different disguise, so it's always a little hard to see. I realize that. Okay. And this is the principal series. Well, you can see it here because what's going on is I have these functions del equals 0. I restrict them to the boundary. This is an isomorphism. And Peter has told you that the discrete series are quotients of this principal series by the constants. Should I say that again? Okay, so I have my space, which I define to be harmonic functions on the disk, which have smooth boundary values. The smooth boundary values are C infinity of the projective line. That's a principal series. That corresponds to S equals minus 1. Right? No, but if you have, I'm worried. You've got me really very, very worried, because if you have to, then the chances are that there's this little cloud of ignorance sort of surrounding the. Somebody else ask another question so we can straighten it out. So the C infinity, on the boundary here, I've got C infinity of P quotient G. This is end of delta minus 1/2. Right. And Peter told you that this principal series contains the constants. Yeah, because this is C infinity. Well, because it's C infinity of G quotient P. So it contains the constant functions. And Peter told you, so this is maybe what Peter told you, that if I take this principal series, I divide by the constants, I get the sum of his two discrete series. Okay, so I'll leave it at that.
The other discrete series,
The what?
the other discrete series that doesn't appear here will consist of functions which are singular at the origin.
No, everything's, it corresponds, in general, the other discrete series are constructed as sections, so these are sections of functions on the interior of the disk. The other discrete series are constructed as sections of, well, the other spaces are related to sections of holomorphic line bundles and anti-holomorphic line bundles on the unit disk.
This is maybe worth the lecture in itself.
Yeah, that may be very well be worth a lecture in itself. It's not, I mean, it's not a trivial step to see that. I'm just saying this is the only case it's really simple because it just does deal with the functions.
Oh, no, I just meant that the principal series has two discrete series parts in it.
Yes.
We see one discrete component right here, and the other discrete component will consist of functions singular at the origin.
I'm not sure. I'm not sure what you mean by that. We can talk about that
So
later.
we have a principal series which consists of function, smooth function on the circle,
Mm-hmm.
and we have a discrete series component which consists of functions regular through the entire disk, more or less, apart from constant.
There's some truth to what you're saying, but I don't want to elaborate on it because nobody else can follow this conversation, I think.
So in simple terms, it means that you have a discrete series here, right?
Yeah.
So another.
The discrete series is a quotient here, though.
So it was this plus something else that was a quotient of the induced representation, right? You have the induced representation as you have two discrete series as the quotient of induced
Right,
representation.
right. That's
So
a,
what is the other one? That's the basic question, right?
oh, I get the two discrete series together. I get remember, I have two different kinds of forms. I have the holomorphic forms and I have the anti-holomorphic forms.
So these are D plus and D minus.
And this is D plus and this is D minus.
Oh, okay.
I mean, holomorphic, one is holomorphically integer, one
Yeah, this is D plus 1 and this is D minus 1. No, but they're both.
No, you could consider the D minus as being holomorphic.
But that's not. That's complicated. There is some way to make that work, but okay, it's much simpler to work with this, I think. Okay. Okay.
So, but for the moment, we are working with them together.
Yes, yes. I'm not separating them, except they do separate because it's the holomorphic ones and the anti-holomorphic ones. Okay.
Your statement that the L2 of these one function of D as one to the L2 of S2R.
I'm sorry, say this again?
Is this, that is this representation into the L2 of one forms.
Yes.
Is your claim that this L2 of one forms is the same as the L2 of S2R?
Contained in. It's a discrete summand. What I'm giving you here is a discrete summand of the square integrable one forms which on D.
Yes. Then you,
It has two different, so what I get is I get a whole thing. I get D plus 1 plus orthogonal sum D minus 1 plus some garbage. And this this turns out to be, in fact, L2 of one forms on D. I haven't told you what the garbage is, and we won't for a while, certainly.
but is this garbage, same garbage if
This garbage is a This garbage what?
is this garbage mean if for S2R you L2 of that you have the same composition, except for we don't know if the garbage is the same.
The garbage is messy. It's a continuous spectrum. It looks like L2 of R.
Well, I think he's saying is there some sort of relation between the garbage here and the garbage on L2 of SL2R?
Yes. Yes. Yes, of course. It's some K-type. It's some specific K-type. What we're doing here, by restricting, by looking at one forms on D, what you're looking at on SL2R are forms which, so if we look at functions on D, we're looking at things which are fixed on the right by K, right? If we look at forms on D, we're looking at functions which are associated to some other K-type on the group itself. So yeah, I can embed my one forms directly into functions on G. I could do that. I don't want to do that. I didn't want to do that until, but yeah, I can do that. Okay. Okay. There's one more thing. So I'm halfway through actually, but I guess let me explain a little bit about what the other thing I want to tell you is. So the reason for knowing about this is because this is when you introduce automorphic forms, this is how the automorphic forms arise. If I look at, am I looking at automorphic forms with respect to SL2Z, for example, then the way you define them is you look at the holomorphic forms of weight 2, for example. This is what they are, and you transform them this way. So this is the realization of the discrete series that has relations to classical theory of automorphic forms. So that's the importance of this particular way of looking at things. We'll talk about that next week. Okay, let's look at the boundary values. So let's just look at C infinity of P, G quotient P. Let's forget about the interior for now. We have a de Rham differential which takes this into the one forms on the projective line. And this is G covariant. Now, this is principal series. Well, this is principal series. And this is principal series. Well, okay. And so what we have here is another intertwining operator. And this is not the previous intertwining operator. So we also have, if you look at the formulas I gave this morning, there is this ordinary intertwining operator as I get by integrating over n. That's perfectly holomorphic here. But this is a new intertwining operator we haven't seen before. It's different from TW, which is still defined. So we have altogether so far then, if you believe this, which is not too hard to show, and I'll show it, I hope to show that in a moment, we have altogether 3 intertwining operators. So if I take my space V to be C infinity of the projective line, then we have, first of all, a map from V into itself. That's an intertwining operator. And this corresponds to the functional, by Frobenius reciprocity, f goes to f of 1. Then I have a map TW, goes to sigma, the omega infinity, and that corresponds to integral of FWN dn. And then we have the differential, the de Rham differential D, and that's another one. So and these are all linearly independent. So in this case, we have that Vn quotient V is at least dimension 3. In fact, it is exactly dimension 3. Okay. So the question is, how does this fit into the scheme of, how can we sort of see this on generic grounds? And I'll just very briefly say something about this because my time is just about up. So what we do is the following. So I have my projective line, and here's infinity in the projective line, which is fixed by P. Now, this picture gives me the Brouillard decomposition. So what we have is we have one P orbit here, and this is isomorphic to n, and then we have a P orbit here, which is just a point. So this corresponds to the Brouillard decomposition. G is equal to P Wn union P. So the decomposition of the projective line corresponds to the Brouillard decomposition. And this intertwining operator, the TW, corresponds to integration over this. And the other one, the lambda 1, or the T1, I guess I can call it, the other one corresponds to somehow to this, which I want to explain. So I just want to introduce one idea, and then I'll be through. So what we do is we put something called the Brouillard filtration on this space. On the space P, quotient G equals the projective line. And it works like this. I define a space, I'll let the whole space be I, so let's call I equal C infinity of P, 1. And I introduce a space IW equals F, functions F in I, such that the Taylor series vanishing, well, the Taylor series vanishes at infinity, or the other way to say it is the functions vanish of infinite order at infinity. So if you want to define, if you want to sort of picture that, then you have the following picture. Here's the projective line, here's infinity, and one of these functions is extremely flat. If you draw a graph of the function on the circle, then it's extremely flat here. Vanishing of infinite order. Its Taylor series vanishes at that point. What's the quotient? Peter? You're raising a hand for some reason? Oh, I thought you just, okay. What's the quotient of all of I? So I take my space I. I is all C infinity functions on the circle. I look at those functions which vanish of infinite order and infinity. What's the quotient?
In the polynomials or power series.
The Taylor series, right. That's right. So we have the following picture. And we'll call this, it is infinity, so it's formal power series in 1 over x. And we can say more about this. So this is what the Bruja, so the Bruja filtration is this subspace included in this, and the quotient is that. That's the Bruja filtration. This is P stable. Each one of these pieces is stable under the group P. It is also stable under the Lie algebra G. Because if I take the derivative of something which vanishes of infinite order, it still vanishes of infinite order. Okay. And now, what's true is that somehow the intertwining operator TW is somehow associated to this part of the filtration, and the other operators, the Ram differential and the f goes to f of 1, are somehow associated to this part of the thing. And this is what we'll explain next week in more detail. So what this leads to is a complete description. So I claim that V mod NV has dimension at least 3, but if we analyze this picture, we'll be able to see exactly understand what that quotient looks like in some detail. And that's a preview of what's coming.